code, we use syntax that looks like a simplified version of English. We type instructions like print, if, and return, but the processor inside your computer cannot read text. To the hardware, those words are invisible. At its most basic level, a CPU only recognizes electrical states, switches toggling between high and low voltages. For your logic to actually execute, there must be a translation system, a bridge that converts human-readable text into raw electrical signals. Consider this basic Hello World program. It's only 5 lines of C code. It is a common mistake to think this text converts into a functional program in a single, immediate leap. In reality, the journey from text to hardware happens across a 4-stage manufacturing pipeline. Navigating these 4 specific stages provides the mechanical context for how software actually interacts with a physical processor. The first stage is the preprocessor. Its role is restricted to preparing and formatting the raw text before any actual translation begins. First, it identifies and deletes every comment you've written. Since comments are for humans rather than machines, they are stripped out to clean up the file. Then it handles the include directives. When it sees standard.io.h, it searches for that external header file and copies its entire contents, thousands of lines of code, directly into your document. At the end of this stage, your small 5-line program has grown into a massive consolidated text document ready for the next step. Stage 2 is compilation. While people often use the word compile to describe the whole process, it technically refers only to this specific translation step. Here, the compiler translates the high-level C syntax into assembly language. Assembly consists of hardware-specific instructions, like push or move. It is much closer to the machine's logic than C, but it is still represented as text. Because the output is still text-based, the compiler cannot produce a final executable. To get to the binary level, we have to go deeper. Stage 3 belongs to the assembler. This is the tool that finally moves our logic from text into the realm of hardware. The assembler takes those assembly mnemonics and converts them into machine code, the actual string of ones and zeros the CPU understands. It then packages this binary data into a container called an object file. However, the file is still incomplete. While your logic is now binary, standard commands like printf don't have their definitions stored here yet. The program has the instructions to call the command, but doesn't actually contain the command itself. This is the final stage, the linker. It plugs in those missing pieces. Common functions like printf live in external precompiled C libraries, separate from your code. The linker maps your object file to the library, binding them into a single unit. By resolving these external references, the linker turns fragmented binary data into a self-contained program. The result of this 4-stage pipeline is the final executable file. We have successfully moved from human-readable text to a machine-executable package through preprocessing, compiling, assembling, and linking. Understanding this hidden manufacturing process reveals the complexity involved in translating a few simple lines of code into actual physical behavior on a CPU.
अच्छी लगी है तो लाइक कर और सब्सक्राइब करो ऐसे वीडियो के लिए।